Yes, we can see perfectly.
Yes, sorry. So good afternoon, everyone. And I would like to thank the organizers of the entire program and also specifically the organizers of this workshop for inviting me to give this talk. So what I'm going to discuss is the dynamics of polymers in random and turbulent flows, and more specifically the phenomenon of the coil stretch transition and its relation with the statistics of the stretching rates in a random flow. So just to set the context, what you can see here in these pictures are the images of polymers in a flow with a weak gradient and in a flow with a strong gradient. So when a polymer is immersed in a flow where the gradient is small or weak, the polymer relaxes to its equilibrium configuration. It takes a coiled configuration. Whereas when the velocity gradient is sufficiently large, it exceeds a given threshold, the polymers can unravel completely and take its full length. And what is interesting is that the transition in this change in conformation of the polymer is not as a gradual function of the velocity gradient, but there is a real transition from one configuration to the other. And this is why this phenomenon is described as the coil stretch transition. And this happens for a critical value of the velocity gradient. So this is the phenomenon that I will try to characterize essentially in the rest of the talk. Just a short, a few words about the outline of the talk. I will start by describing the modeling, how polymers are usually modeled in this context. I will discuss the phenomenon of the coil stretch transition in more detail in the case of extensional flows, because this is where it was first predicted and observed. And then I'll come to random and turbulent flows. So I will start by reviewing what is known about the statistics of the deformation of a polymer. And then I'll come to some more recent results about this same problem. So to start with, there are two dimensionless parameters that describe a polymer molecule in a flow. The first one is the ratio of length scales, where our equilibrium is the size of the polymer when the fluid is at rest. So the polymer is not deformed, it's the end-to-end separation. And L is the maximum length of the polymer. So the ratio of the two squared is known as the extensibility parameter. And in most applications, this extensibility parameter is fairly large. So there is a large separation of scale between equilibrium and the full extension. The second dimensionless parameter is the Weissenberg number, which is a ratio of time scales. So when the polymer is immersed in a fluid at rest and it is stretched, its extension relaxes exponentially to the equilibrium extension. And this defines what is known as the relaxation time of the polymer. When the fluid is not at rest but in motion, and there is and it is not homogeneous, there is a velocity gradient, one can associate to the velocity gradient a stretching time. So the ratio of the relaxation time of the polymer and the typical stretching time of the flow is known as the Weissenberg number. So small Weissenberg numbers mean small deformation because the polymer relaxes very fast to equilibrium, whereas large Weissenberg numbers mean that the polymers takes a long time to relax to equilibrium. So the flow is effective in deforming the polymer, and one observes large extensions. Now, how does one usually, how polymers are usually modeled in this context? So the most common way is a coarse-grained description of a polymer molecule as a sequence of beads connected by elastic springs. So the forces, the interaction between the flow and the polymer are concentrated on these beads. And each of these beads is subject to 3 forces. First one is the Stokes drag with the Stokes coefficient zeta. Then there are the collisions with the molecules of the fluid, and this is modeled as a white noise. And third, it's the elastic force due to the presence of the springs. And these coefficients here depend on how we model the elasticity of the molecule. The most common ways are the following. The simplest one is a linear elasticity. This is useful in theoretical studies, but it's unphysical because in principle it allows infinitely long polymers. If one wants to impose a finite extension for each of the links and therefore for the entire molecule, one can consider nonlinear forces that diverge when the size of a link reaches a maximum fixed length. The first example is what is known as the finitely extensible nonlinear elastic force, and it is more appropriate for synthetic polymers. The second one is the Markov-Sidja law, which is usually employed for biological molecules. There are 3 more assumptions. One is in the most basic version of these models, hydrodynamic interactions between the beads and excluded volume interactions between the beads are neglected. This is particularly meaningful when one considers extensions, when one considers large extensions, because the beads are far apart. And so the segments of the molecule have weaker interactions between them. And inertia is usually neglected. The Stokes number of a molecule, of a polymer molecule in a turbulent flow is usually of the order of 10 to the power minus 6. And the polymers are usually smaller than this. The size of a polymer is usually smaller than the smallest length scale of the flow, which means, for example, in turbulent flows, polymers are usually below the viscous scale. There are exceptions to this at very large Weissenberg numbers, but in the most common cases, this is true, which allows to describe the velocity differences between the beads in terms of the velocity gradient alone. There is one further and very strong simplification, which is usually done in the analysis. One, instead of considering n beads, one can move to an even simpler model where only 2 beads are considered. And this is known as the dumbbell model. In this case, the 2 beads should be interpreted as the ends, as the end beads of the molecules. And the spring would model the entire elasticity of the polymer. In other words, when one considers the dumbbell model, one is focusing on the slowest of oscillation mode of the polymer. And the description in this case reduces to a very simple stochastic equation where we recognize the 3 forces I mentioned earlier: the stretching by the velocity gradient due to the linearization of the flow, then the elastic force, which could be nonlinear depending on how we choose this coefficient, and the thermal noise. There is if this is a microscopic equation, there is an equivalent macroscopic equation in terms of a diffusion equation for the probability density function of the separation vector between the beads. And the other point I want to make is that despite the extreme simplification of this model, it is widely used, and it is the basic ingredient for continuum models of polymer solutions. So despite the many simplifications, it has proven quite successful, at least for a qualitative understanding of single polymer dynamics in general and also polymer solutions. Now let me come to how this model has been used to predict the coil stretch transition, first in a laminar extensional flow. So this is a very simple argument. One takes an extensional flow with a compression in the x direction and extension in the y direction. The Weissenberg number is defined in terms of the amplitude of the gradient and the relaxation time of the polymer. If now we assume linear elasticity, so F equal 1, and we neglect the thermal noise, so the X and Y component of the separation between the ends of the beads decouple, and one can see that in the compressing direction of the flow, there is exponential decrease of the extension of the polymer, whereas there is a full stretching, exponential stretching, or exponential compression in the Y direction, depending on the sign of this coefficient, which can be rewritten as a difference between the Weissenberg number and the critical value, which is 1/2. So below this 1/2 value, there is exponential relaxation to equilibrium, and beyond it, there is exponential increase. This is the essence of the coil stretch transition in an extensional flow. Of course, this was based on assuming F equal to 1. If one wants to, this exponential increase in a real system would not continue for an infinite time. When nonlinear effects come into play, then the extension will stop. And to capture this, as I mentioned earlier, one can consider a nonlinear force which diverges for a maximum length L. So if one does this, one can capture also the regime for large Weissenberg numbers beyond the transition, and one can observe indeed a strong increase in the rescaled extension of the polymer, rescaled by the maximum length, beyond the value which is 1/2. It is also possible to calculate the exact PDF of the extension in this simple model. There is one point that I would like to make and try to remember for the following part of the talk. And this is, this PDF displays an arrow peak, which is either around the equilibrium size 4 Weissenberg numbers below critical, or beyond it, or close to the maximum size 4 Weissenberg numbers beyond the critical value. So it's only around the coil stretch transition, there is a widening, a broadening of this PDF. So it's rather either a peak on one side or a peak on the other side. And we will see that the situation will be completely different in a random flow. So I'll conclude this part on the extensional flow here. I just want to mention that it has been observed in experiments. And this coil stretch transition that is observed for extensional flows does not exist for a shear flow. For a shear flow, when we increase the Weissenberg number, so the amplitude of the shear, we obtain only a gradual increase in the extension, not such an abrupt change in conformation. And the reason for this is that in a shear, there is an equivalent amount of stretching and rotation. So the polymer is not persistently aligned with the direction of stretching, but rotation can move it away from the stretching direction, and therefore make the polymer collapse again to its equilibrium extension. This observation, in particular, about the difference between extensional and the shear flows, bring us to random flows, because the question arises now, can we see a coil stretch transition in a random flow, given that in a random flow, we do have rotation, and the stretching direction of a random flow fluctuates both in direction and in intensity. So is a random flow able to stretch a polymer? So the answer will be yes, though there will be different features in the statistics of the polymer. And a first positive answer to this question was indeed given by Lumley a long time ago, where he recognized, again, based on a simple dumbbell model with linear elasticity, that if the product of the RMS strain, of the mean square strain, and the Lagrangian correlation time of strain is greater than 1/2 tau, then there can be complete unraveling of the molecule. So you recognize here in a more, let's say, modern language, that here there is a notion of Lyapunov exponent. So if we define a Weissenberg number based on the Lyapunov exponent for a random flow, then we should expect complete unraveling and therefore a coil stretch transition in the polymer. So it is only much more recently that indeed this idea was put into a more systematic context in the language of dynamical systems. And this is what I'm going to discuss briefly. So very quickly, because of course all of you know extremely well the following. As you know, when one considers a line element, the rate of exponential increase of a line element in the flow is given by the Lyapunov exponent. Then one can define not only the Lyapunov exponent, but a sequence of generalized exponents, which are the moments, which is the rate of exponential growth of the moments of the line element. And this defines a function of the exponent Q, which is convex. Its first derivative at the origin is the Lyapunov exponent, and in an incompressible system, at minus d, it vanishes. D is, of course, the spatial dimension of the flow. And when the distribution of the line element, of the size of the length of the line element is log normal, this function is quadratic. This is something well established also in turbulent flows. These references describe the statistics of line elements in detail. So now by using this formalism, these tools, Balkovsky, Fuxon, and Lebedev made probably one of the most important predictions about the deformation, the statistics of the polymer deformation in a random flow. Their theory is based on the large deviation formalism for the stretching rates, for the statistics of the stretching rates. So on the Cramer function, equivalently, this can be reformulated in terms of the generalized Lyapunov exponents, and this is the formulation I'm going to use. They considered intermediate extensions between the equilibrium and the maximum length of the polymer and a simple dumbbell model. And they observed that the PDF of this extension must follow a power law behavior. So you immediately see a strong difference with the extensional flow, as I pointed out initially. We don't have a statistics dominated by a narrow peak here, but a broad distribution with a power law behavior. And what is interesting is that this exponent with this alpha that appears in the exponent is related to the generalized Lyapunov exponents through this equation. So now let us look at this, at the solution of this equation, because a lot can be inferred from the properties of L of alpha, which I mentioned earlier. So L of alpha is here rescaled by lambda for convenience, is this convex function, which is vanishes in minus t and as a slope equal to 1 at the origin. So I have to intersect it with this straight line whose slope depends on the Weissenberg number. So when the Weissenberg number is large, the intersection happens at positive alphas. So this makes the PDFs steeper than -1. Then when the slope of when I increase Weissenberg, the slope decreases, and so the intersection moves to the origin. And it becomes alpha vanishes when the Weissenberg number is exactly equal to 1/2. If I increase Weissenberg further, alpha becomes positive, and this PDF becomes less steep than r⁵ -1. So this was recognized as a critical value of the Weissenberg number, again 1/2, because if we take the L going to infinity limit, which is we take a linear elastic polymer, this PDF is not normalizable anymore beyond 1/2. And so this was considered as a sign of a coil stretch transition, in the sense that the probability of finding stretched polymers suddenly becomes larger and larger as the Weissenberg number exceeds this threshold. And an interesting thing is, as you know, in a turbulent flow, for example, in an intermittent system, this function deviates from the quadratic log normal expression. But at the same time, the deviation is usually observed. The most important deviations are observed for large values of the moment. So here, for large values of positive alpha. However, this region is less interesting for us because the most, as we saw, the most of the dynamics happens here when the Weissenberg number is beyond the coil stretch transition, so it's here, or slightly below. So large deviations will be observed only for very small Weissenberg numbers, which is not a very interesting regime. So it is interesting to look at what happens when we have a log normal distribution, so in the vicinity of the coil stretch transition, but we don't expect large deviations far from it. In this case, we can use this quadratic approximation and calculate alpha exactly from this expression. So, as I said, in this approach, when one considers only, when one neglects the existence of a maximum extension, the PDF becomes non-normalizable. But of course, this is not physical. One can also improve this theory, complete this theory by including a finite extension for the polymer, and so a non-linear elasticity. And if one wants to achieve a fully analytical calculation, one can make assumptions on the random flow that transports the polymer. So let us back to the stochastic differential equation for the separation vector. We now assume a nonlinear elasticity, and we have an associated Fokker-Planck equation. Now, if grad U, we want to model grad U in a simple way, this becomes a stochastic multiplicative term in the equation. And the simplest way is to use what is known as the Bachelor-Crichton flow, where the velocity gradient is basically a tensorial white noise with the coefficient here that ensures the incompressibility and isotropy of the system. In this case, the PDF of the vector R becomes a PDF both with respect to both noise and the statistics of the velocity gradient. And since the flow is isotropic, we can expect that this PDF only depends on the size of the separation vector, not on its orientation. So the problem simplifies considerably to that of a Fokker-Planck equation in one variable only. Now, with some drift and diffusion coefficients, and with the reflecting boundary conditions at R equals 0, because R cannot become negative, and R equal to the maximum length, so because R cannot, again, absorb reflecting boundary condition, because R cannot exceed L. So if we use that, we can obtain an exact solution for the PDF of the extension when we recognize the three regimes. The first is just the regime where which prevails, it's the regime of small extensions, which are dominated by thermal noise. The last one is a cutoff, which is imposed by the maximum extension. And the intermediate one is the prediction I mentioned before. It's a power law behavior with R to the power D minus 1 minus 2H, which gives the value of alpha that we discussed in the previous slide, because in the Bachelor-Crichton flow, the statistics of the elementary length, the length element is log normal exactly, not only near to the coil stretch transition, but for all Weissenberg numbers. Now, as I mentioned, if we plot this PDF, you see a complete different shape compared to the extensional flow. So the typical for a typical Weissenberg number, this PDF is a very broad shape, which indicates that there is a coexistence of coiled and stretched polymers in the flow, and the Weissenberg number only determines which configuration prevails. We don't have a dominant narrow peak that moves from one side to the other, but rather it is the slope of the power law that changes. Nevertheless, this gives a coil stretch transition, a sudden increase in the extension or in the position of the maximum extension. Now, this bachelor Crankton flow has been used a lot in the past to study polymers. It is interesting to analyze its limitation. The first one was the delta correlation time. It's white noise, so it has a zero correlation time. But if one study, for example, polymer stretching in a renewing flow, where the correlation time can be changed independently on the Lyapunov exponent, it is possible to see that the value of the exponent alpha, the slope of the PDF, of the tail of the PDF, remains basically independent on the correlation time of the flow for correlation times of the order of 1 over lambda, 1 of the Lyapunov exponent. So the predictions remain relevant for a turbulent flow, for a realistic flow. And the second point is the Gaussianity of this system, of the Batchelor-Crankton flow, which is different, which is not found in a real turbulent flow. But if we compare here alpha in a DNS of isotropic turbulence with the prediction for a log normal, with the log normal prediction, we see only small deviations. And the reasons are what I mentioned before, that the region which is really relevant for polymer stretching is the region where the deviations from the quadratic expression for the generalized Lyapunov exponents are not so substantial. Huge, important differences would be found only at very large values of alpha, so for very large positive values of alpha, so for very small Weissenberg numbers, which is not the most interesting part. Nevertheless, there are small chain differences, and it's interesting to discuss their physical meaning. Indeed, for small Weissenberg, we see that the DNS has a smaller alpha, which means a larger -1 minus alpha. So the Gaussian, in a Gaussian flow, the PDF of extension is steeper than in the case of DNSs. And this is because at small Weissenberg numbers, large extensions, so the power law, the tail of the PDF, so extensions in the tail can be obtained only for large values of the velocity gradient. And so one needs large excursions of the velocity gradient. And this in a turbulent flow happen more frequently. So somehow the intermittency of the flow is useful to obtain larger extensions at small Weissenberg numbers. The opposite is true at larger Weissenberg numbers, because there a Gaussian flow, so the relaxation time of the polymer is longer, so a Gaussian flow is more effective it's a more persistent persistently stretching the polymer, whereas having very strong but rarer excursions is less useful in this case. So let me now move to simulations. This was the theory. In the simulations, The power law behavior of polymers is also very well confirmed now. It was initially done for linear polymers and later for also non-linear polymers in various flow configurations, going from a turbulent shear to turbulent channel flow and also isotropic turbulence. In all cases, this power law behavior and its functional dependence on the Weissenberg number is well confirmed. And in addition, also in the case when the feedback of polymers is taken into account, a similar power law behavior has been observed in these simulations from Rahul Pandit's group. What about experiments? Sorry, before coming to experiments, I also wanted to make this important point. When we have, so I mentioned that we have been using the dumbbell model to obtain all these results. It is a crude approximation of a polymer molecule, but it works well. Indeed, if one applies a proper mapping of the maximum extension of the links of a full chain, if one considers a chain with a proper mapping of the parameters in terms of the full length of the chain and its relaxation time, one can see that there is good agreement with the dynamics of a full chain and a dumbbell model. Here are simulations by Watanabe and Goto for n equal to the dumbbell and 20b the chain. And one can see that there is good agreement in the shape of the PDF, in the mean extension of the polymer as a function of the Weissenberg number, and in the correlation time of the extension of the Weissenberg number. This mapping was due to Ginn and Collins, and it's interesting to see in this simulation how indeed a chain, which we will see in green, behave approximate in how a dumbbell approximates a chain quite well. You will see deviations in the orientation sometimes, but the statistics of the extension is pretty well reproduced by a dumbbell model. So then now coming to experiments and how this power law behavior has been observed. These experiments were mainly done in the group of Victor Steinberg. Since polymers are microscopic objects, one requires microfluidics devices. And to reproduce a random flow in a microfluidic device, which is generally described by very small Reynolds numbers, Victor Steinberg used as a fluid a polymer solution at high elasticity, and by using elastic purely elastic instabilities, the flow became he was able to obtain a random flow known as elastic turbulence. And then to directly observe the behavior of a polymer and calculate the statistics of the extension. And this power law behavior was confirmed with a power law that increases in slope from negative to positive as a function of the Weissenberg number. So these experiments confirm the existence of a coil stretch transition also in a random flow. They confirm the fact that this coil stretch transition exists, but of course it's not as effective, as strong as in an extensional flow, because stretching is not persistent in time in a random flow. So this somehow concludes this summary of results of which I wanted to make. And I'm now coming to some more recent results that we have obtained in the past couple of years. So the first one is an alternative characterization of this coil stretch transition, which uses the notion of entropy, of information entropy or Shannon entropy of a stochastic variable here, which is here the extension rescaled by its maximum length. So it was already suggested earlier to study the entropy as a function of the Weissenberg number, this entropy as a function of the Weissenberg number in an extensional flow, and much more recently in the random flow experiments of Steinberg and co-workers. And we have already observed that in both cases, the PDF of the extension broadens near to the coil stretch transition. This means that there is a wide range of possible polymer configurations. And this means that there's if you want, a loss of information in the system. And so it is expected and confirmed in these cases that there is a maximum of Shannon entropy in near to the coil stretch transition. So what we did is to make a kind of comparative study of this phenomenon by looking at this entropy of the rescaled extension for different flows. And this observable to describe the coil stretch transition is quite useful from a practical point of view, especially in experiments, because in the end, this is a mean quantity. And whereas criteria based on the PDF of the extension require a very good resolution of the slope of this PDF, which means very good statistics, and which in turn is not always available in an experiment. Since this is a mean quantity, less resolution is needed to measure it in a sufficiently accurate way. And so, since this is a scalar quantity, it is now nice to see how it condenses information, how this condenses information on the coil stretch transition on a single scalar information. So here we have how this curve behaves for an extensional flow, a turbulent flow, a shear flow in green, and then the bachelor Kirkland flow in blue and the turbulent flow in yellow, and the experiments in black. Although this, of course, is a fit of a dumbbell model with the maximum length as a parameter. So as you can see, a very narrow maximum is only observed the extensional flow. Indeed, it's only in this case that on each side of the coil stretch transition, we have a narrow peak in the PDF, and the broadening only over a very narrow range of Weissenberg numbers. For a shear flow, as we mentioned, we don't have a coil stretch transition, and therefore we don't really see a pronounced maximum in the shear rate, only a gradual increase with the Weissenberg number. In random flows, we do see a maximum because we have seen that there is a maximum coil stretch transition, but this maximum is the entropy is always greater than in the case of the extensional flow, and this has to be attributed to the fact that the distributions are broader in the random flow. Moreover, the maximum is wider than in the case of the extensional flow because the coil stretch transition occurs on a broader range of Weissenberg numbers. It is not such an abrupt phenomenon as in an extensional flow. Also, we see a remarkable comparison between the bachelor Kirkland flow and the turbulent DNS of isotropic turbulence, which could be expected based on what I said earlier about the effect of a zero correlation time and the effect of a Gaussianity that only leads to small deviations in the statistics of R. This difference at large Weissenberg numbers is due to the fact that in a turbulent simulation, we can go back here. In a turbulent simulation, the PDF of R is able to show a large, kind of narrow peak at large extensions, which is not present in the Kirkland flow because the stretching, due to the delta correlation in time, the stretching is never persistent enough to generate such a peak. So this is why in a random flow, distribution remains wider for large Weissenberg numbers, and so the two curves diverge at large Weissenberg numbers. So, so as you can see, a lot of information can be gained from this quantity. Just one more remark on this picture, on this plot. As you can see here, though, the maximum is not exactly at 0.5. How to reconcile then this difference? Well, the reason is that the appropriate observable for a random flow is not the entropy of the extension, but of another function. If we go back to the diffusion equation for the PDF of the rescaled extension, in a random isotropic flow, we can make an argument a la Richardson and describe this term, the stretching term, by means of an eddy diffusion coefficient, which will scale as rho to the power 2, because the flow is smooth at the scale of the polymer. So as you can see, we will have a diffusion coefficient which is which depends on the random variable. So we are studying a transition where the coefficient of the noise depends on the variable itself. And this is probably not the best way to study a transition in terms of a control parameter, which is then depending on the variable itself. So it's more appropriate to make a transformation variable which transforms the diffusion coefficient into a constant which will depend on the Weissenberg number, and then use which will be a function of the Weissenberg number, and use the Weissenberg number as the control parameter. So this transformation of variable is a logarithmic transformation. So the appropriate quantity in a random flow is the entropy of the logarithm of rho, which is not surprising given that we're basing our study on the Weissenberg number, which is defined in terms of the Lyapunov exponent. If we consider this other observable, we do see that the maximum of the random curves move to 1/2, which was the critical Weissenberg number. Let me now come to another point. If we look at the theory for the slope of the PDF, we have said that we have this alpha is given as the intersection between this straight line and the generalized Lyapunov exponents. So when the Weissenberg number tends to infinity, this line becomes horizontal, and the intersection tends to -d, minus the dimension. So the slopes tends to d-1, and therefore in a three-dimensional flow to 2 r². However, in the experiment at large Weissenberg numbers, one can see slopes as large as alpha equal to -5, so r to the power 4, much larger than 2. How to explain this? So a possible explanation is given by considering internal dissipation mechanisms in the molecule. One can imagine that the stretching and collapsing dynamics of the links is dissipative, or that there are frictions between different segments of the molecule, which would be far apart but come close to each other during the dynamics. So this is usually described by means of a phenomenon which goes under the name of internal viscosity. So this is introduced in the dumbbell model and in bead spring chain models by means of a dashpot together with the spring, which would make the spring dissipative. And with a coefficient, which then is a dimensionless coefficient, which is the ratio of the amplitude of this dissipative function over the Stokes drag. So it so happened that if we take the larger deviation theory and introduce this additional force, our equation for the slope is modified in this very simple way. And so this solution is just a multiplication of the slope by a factor 1 plus epsilon, where epsilon takes into account, takes these dissipative mechanisms into account. So if we do so for large Weissenberg number, the PDF behaves as r to the power, at a large Weissenberg, yes, it becomes d to the power 1 plus epsilon minus 1. And we can recover the r to the power 4 with epsilon equal to 2/3, which is completely compatible with the values which are usually used in modeling and simulations, and which reproduce other phenomena in polymer dynamics. So this steepening of the distribution at large Weissenberg numbers compared to the theory seems to be attributable to internal dissipation mechanisms in the molecule, which make the distribution less broader. So deviations from the mean less likely. Another mechanism, as you can see now that we have this simple model and this formalism of the Batcheller-Kalkin flow, one can modify the formalism, one can modify the model to introduce new mechanisms, new phenomena in the system. And another one is the possible scission of the molecule. Indeed, in a turbulent flow, a molecule is a subject to very large gradients, and these gradients can break the links of the molecule. One simple way, very simple again within this coarse-grained description, of course, from a chemical point of view, studying the scission of a chemical link is something much more involved. But at this level of a coarse-grained description, one can assume that when the tension in one of the links becomes greater than a given threshold, the link breaks. And one can also do this this is equivalent to saying that there is a critical length for breakup in each of the links. If one does so, one simply has to go back to the Batcheller-Kalkin description and now introduce an absorbing boundary condition at the critical length for breakup. And if for simplicity now we assume a monodispersed initial condition, because now the system is not stationary anymore and the initial condition plays a role, initial distribution of polymers plays a role. So based on this framework, we can make some simple prediction and compare them with simulations, Lagrangian simulations of isotropic turbulence with chains in this isotropic flow. So the first one is that the number of polymers decreases exponentially in time with the characteristic time scale, which is given by the smallest positive eigenvalue of the Fokker-Planck operator. This is well reproduced in simulations with of a large ensemble of polymers with n beads, and the typical decay time decreases very rapidly beyond the coil stretch transition, which can be confirmed by looking at the positive again at the smallest eigenvalue of the Fokker-Planck equation. Then one can consider not the so now the PDF is now a time-dependent quantity because the system is non-stationary, but one can calculate the time-integrated PDF, which will be useful in a minute for another important quantities. And this PDF now displays 3 different power law behaviors. So there is a one range between 0 and the equilibrium length, which is fully dominated by thermal noise, and this is the usual r to the power d-1. Then there is an intermediate range between the equilibrium length and the initial condition, initial length, provided of course this is greater than the first. And here we recover the usual prediction with the alpha given as before by the large deviation prediction. But now we have beyond the initial condition and the breakup length, we have a new power law, which below the coil stretch transition is the usual alpha. So nothing happens basically until very near to the breakup length. But beyond the coil stretch transition, this exponent becomes exactly 0 for all values of the Weissenberg number. And so the PDF behaves as r to the power -1 for all Weissenberg numbers. And this, as you can see, is very well confirmed in numerical simulations. So this, in addition for being a nice analytical result, it is also useful because one can calculate the average scission time, so the lifetime of a molecule before the first scission. And this mean quantity is related to this time-integrated PDF of the extension. If we now insert those asymptotic behavior in this integral, we can calculate this expression, this mean scission time, below and above the coil structure transition. And we observe two different behaviors, a power law behavior below the coil structure transition and the logarithmic dependence on the behavior as a function of the maximum length of the polymer rescaled by its initial length. Whereas beyond the coil structure transition, this mean scission time depends only logarithmically on the maximum extension of the polymer. This is well confirmed by simulations. And the simulations, in addition, tell us that not only the mean, but the distribution of this scission time, which is exponential, is a function which is exponential for all Weissenberg numbers. So one last comment. All that I said up to now was about the steady state statistics of the polymer. It is interesting to see, and this is ongoing work, that this power law behavior of the PDF, also of the PDF of the extension, also exists at finite times. So if we start from an initial condition, which in this case is the distribution that one would have in the absence of flow, 0 Weissenberg, quickly the PDF moves to a shape with a power law tail that then converges to its steady state value. This is seen both below the coil stretch transition and above it. Simply the difference is that in one case the slope is negative, and at a large Weissenberg it is positive. So interestingly, one can see that this exponent alpha converges to its steady state. This convergence is exponential. So of course there is an initial transient that will depend on the initial condition, because if I start from this initial condition, alpha will the slope will increase. If I start from a very stretched initial condition, alpha will decrease. But after this initial transient, there is an intermediate transient, if you want, which is exponential in the way alpha converges to its steady state values. And what is important is that this defines a typical relaxation time to equilibrium. And it's interesting to note that this equilibration time or relaxation time of the PDF, of the tail of the PDF to its steady state, reaches a maximum near to the coil stretch transition, and then decreases rapidly as Weissenberg to the power -1. So there is a slowing down, if you want, of the stretching dynamics of the convergence to equilibrium near to the coil stretch transition. And this is consistent to other previous studies which had analyzed the different variables, like the correlation time, for example, of the extension as a function of Weissenberg. And they also showed a similar behavior. Near the coil stretch transition, as we have seen, so the explanation, the physical intuition is that near to the coil stretch transition, there's such a broad distribution of polymers that in some sense the system requires a long time to fully explore all possible configurations and therefore reach the steady state. So I will now skip the last point and come to the conclusions. Instead, so what I think the message I tried to convey is that a lot on the dynamics of polymers can be understood from these simple models, And by modifying introducing new elements, new phenomena, we can capture, make new predictions and capture new dynamics. Instead of now summarizing this, I think the point I would like to make is that the models which are used to describe polymer solutions of viscoelastic effects like turbulent drag reduction and elastic turbulence are based on the most simple version of the dumbbell model, where there are no hydrodynamic interactions, no breakup, no internal viscosity, no higher order oscillation modes of the molecules, etc. So a big part of future work would be a big goal would be to introduce these new elements in continuum models of polymer solutions, and in order to achieve better quantitative agreement with the experiments and realistic situations. So I'll stop here and I'll thank you for your attention.
Okay, so thank you very much. Are there questions from the audience? Comments?
Thank you. Very nice talk. I was wondering if shear thinning and shear thickening can be studied, included in this context.
Yes, yes. These are phenomena which are typically captured by these simple models, coarse-grained models. And as I said, however, a full quantitative agreement usually requires some fitting of the parameters, and perhaps because some of these phenomena are neglected in the models. But definitely, yes, these simple models I described are the basis for studying the phenomenon that you cited. Yes.
Yeah, but I mean, can you study this like as a function of Weisenberg in more realistic flows?
Yeah, yes, this is well known. I mean, it's done. Yes.
Okay.
Yes. Because as I said, one can construct continuum versions of these models, which are just an evolution equation for a conformation tensor, for a tensor. Coupled with the Navier-Stokes equations. So there is an extra stress in the Navier-Stokes equations due to polymers, and this can lead to non-Newtonian phenomena.
Yes. Okay. Thank you. Other questions? Yes.
So very nice talk, Dario. This in the continuum model which you referred to,
Yeah.
with the how would you put in this dash spot or internal friction? Is that been done already, or?
Not that I know, not that I know, and I would say I don't think so. It should be relatively easy. I think it might. Now I would have to see the equations, but it might require some closures in the same spirit as FNP, as you know, but it should be easy. Yes. I mean, at least in some approximated way, I believe so. Yes.
Thank you.
Okay. So other comments from the online participants? No questions. Okay, so let's thank again the speaker, and let us resume after the coffee break.
Thank you.